Hello and welcome to the 6th of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dennehy, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be your moderator for today's webcast. The idea to have these hour-long webcasts originated from the members of my NESC, GNNC technical discipline team, who thought they would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community practice. We plan to routinely hold these webcasts on the third Wednesday of every other month at this same time, 2 p.m. Eastern. I'm now very pleased to introduce today's speaker, Scott Starin from NASA's Goddard Space Flight Center in Greenbelt, Maryland. Scott has worked at Goddard since 2000 in the areas of spacecraft dynamics analysis, modeling and simulation, vehicle guidance and control, and onboard automation. Scott has provided GNC engineering support to several of NASA's robotic spaceflight missions, such as WMAP, ST-5, ST-7, GPM, and STO. Since May of 2011, he has served as an associate branch head for Goddard's Attitude Control Systems Engineering branch. I'd also like to point out that Scott contributed the update to the Attitude and Control Systems section of the 2011 textbook, Space Mission Engineering, the new SMAD, edited by Wirtz, Everett, and Puchel. The complete version of Scott's bio is provided on the webcast registration site for your reference. Scott's talk today is entitled Fundamentals of Spacecraft Attitude Control. I hope you will find it informative. At the end of Scott's talk, 10 minutes will be reserved for a question and answer period that I will moderate. And now, without further ado, I'd like to turn the webcast over to Scott.
Thanks, Neil. Hi. It's a pleasure to speak to you all here today. I've got here a very rough outline of what I'm going to be talking about in the presentation. This can give you an idea of if there's something missing that you're interested in. You can start thinking about the sort of questions you want to ask. I want to acknowledge the help of several people who contributed slides and information for this presentation. Then I'll get into an introduction to spacecraft attitude control and proceed from there into a discussion of the elements of designing an attitude control system for a spacecraft. Some of those elements are the design process and how it relates to requirements, the disturbance environment that spacecraft exist in. I'll touch briefly on attitude determination, but there will be future webcasts on that topic. Stabilization, controller design, a bit about errors, and then just a little bit about flexible body dynamics and jitter and the effects of that on spacecraft. Again, I'm hoping that there will be a future webcast on the topic of jitter and how it applies to spacecraft. And then I'll talk just a little bit about I'll contrast 3 example spacecraft, big, medium, and little. Then we'll take questions. I also want to direct your attention to the fact that once you have access to this presentation online, there are quite a lot of reference charts at the end of the presentation after the final slides that you'll see today on coordinate systems and on specific kinds of attitude control system hardware. So I'd like to acknowledge the input of Jim O'Donnell, David Ward, David Mangus, and Lou Halleck, who are all here at Goddard. They have, over the years, built up a presentation that is given every other year to a graduate class at the University of Maryland as a lecture on attitude control. And I've borrowed a lot of information from that lecture to include in this presentation. Another source of material is the section on attitude determination and control that I helped rewrite for the 2011 Spacecraft Mission Engineering book that Neil mentioned. And I also want to thank Alice Liu and Carl Blaurock for providing information so that I can talk about jitter in an interesting way, referring to some on-orbit data from the Solar Dynamics Observatory. I want to talk a little bit about what attitude is. Perhaps for a lot of the audience, this is going to seem redundant, but I want to get everybody in the same frame of mind. Attitude is a three-dimensional orientation of a vehicle with respect to a reference frame. And this applies to aircraft, reentry, rockets and spacecraft, any vehicle, this is the orientation with respect to whatever reference frame the vehicle is traveling or needs to know it's pointing. For spacecraft, common use of a spacecraft is as a telescope that can point in various directions in space. So an analogy can be seen to a telescope on a hill on the Earth. On the Earth, the telescope is limited to changes in elevation, 1 degree of freedom, and changes in azimuth, a 2nd degree of freedom. And that allows the telescope a view of the half of the sky that's available to it. In space, the spacecraft would perhaps have the view of the other half of the sky, so 4 pi steradian coverage. But attitude, and so the Earth telescope has 2 degrees of freedom and is therefore described fully by a unit vector. So the unit vector is 2 degrees of freedom, but does not fully describe the attitude of a spacecraft, because a telescope in space may also rotate around its own bore site to important effects. Many space telescopes have pixelated optical planes, and failing to control the rotation about the bore site carefully could result in blurring or distortion of images. So it's important to make sure that that control is maintained. And so in general, even if they aren't space telescope missions, in general, space missions do have to consider all 3 degrees of freedom in their designs. They may not control all 3 degrees of freedom, and we'll look at that in the next slide. So attitude-controlled goals and reference frames. As I said, an attitude is the orientation of a spacecraft, of a vehicle, with respect to a reference frame. Most spacecraft missions have some need for pointing 1 or more pieces of hardware at 1 or more targets, and this may need to happen simultaneously. Solar arrays, for example, need to be illuminated in order to provide power to the spacecraft. Antennas that are used for communication have to point at targets on the ground or at TDRS tracking satellites. Of course, scientific instruments have to point at their targets, whether that be at the Earth or at some star or black hole or what have you. Some spacecraft spin rather than holding steady, and they often require that the spin axis lies along a certain direction. Typical goal for an attitude control system is to point an instrument at one target and to point another piece of hardware, such as the solar array or an antenna, as close to another target as possible. And so it's important to choose the proper reference frame that relates in some meaningful way to the targets that need to be tracked. Since communication satellites, for example, often point their antenna arrays at nadir almost all the time, certainly their goal is as close to 100% of the time as possible. They often use a local vertical, local horizontal reference frame, so that the spacecraft has one axis directed along the local vertical, and then rotations about that axis can be made to maximize solar power. Another example is astrophysics satellites that need to maintain a constant attitude relative to the stars. A good reference frame for those would be an inertial reference frame, such as the J2000. So let's talk a little bit about the difference between spacecraft and aircraft control. I did my best looking for images online of a spacecraft and an aircraft. This spacecraft is the TRIM, the Tropical Rainfall Measurement Mission. It's still flying, and the Global Precipitation Measurement Mission, GPM, is being built here at Goddard and will be its replacement. TRIM flies in a low Earth orbit, and its axes are roughly the same as an aircraft is going to be. So it has a velocity direction along the x-axis, and its z direction is pointing at nadir. So you can think about the attitude of this spacecraft in terms of roll, pitch, and yaw in just the same way that you would an aircraft. But that's where the similarities end. What's needed to control a vehicle in free fall that's not in an atmosphere is very different from the thrust lift combination that you need to have for an aircraft. Disturbance torques on spacecraft are much, much smaller than on aircraft. If we saw a disturbance torque of 1 millinewton meter, then we would consider that a very large disturbance for a spacecraft. Free fall, the dynamics that spacecraft see is neutrally stable, but air flight is not. Even in the best controlled aircraft, there are going to be some unstable modes that need to be stabilized in some kind of an active way. Air provides a ready sink for mechanical energy. So damping of motion that's undesirable is not too much of a concern for aircraft, whereas for spacecraft, there's no place for any vibrational energy to go, and so very small motions can result in jitter and blurring on the images that spacecraft are trying to acquire. So when we combine all of this together, spacecraft can achieve, in general, much better pointing accuracy than an aircraft can, but with very low bandwidth controllers. The lack of damping and low bandwidth, however, mean that spacecraft are susceptible to jitter. Here's a diagram of an attitude control system. We'll touch on most of the blocks in this diagram today. But basically, if we start at the lower right-hand corner, the spacecraft dynamics are essentially the plant, and then internal and external disturbance torques affect that plant. We use attitude sensors on board the spacecraft to estimate an attitude. There are often two different estimates that are made, definitive estimate made on the ground and a real-time estimate made by the spacecraft. And these may be of different accuracy. The onboard estimate of the attitude is fed into onboard control laws, which may be implemented either as analog circuitry or much more often these days as software that's onboard a microprocessor on the spacecraft. Whatever the implementation, control commands are issued in the form of either digital commands or analog signals to attitude actuators. And those actuators affect the control torque on the spacecraft, and this loop is complete. Now I'm going to get into attitude control system design for spacecraft. The basic steps can be outlined in this way. We often define control modes, and control modes are basically different ways that the attitude control system will need to operate in order to meet different regimes of system-level requirements. For example, to acquire science information, one mode may be necessary to keep a spacecraft extremely stable in its pointing, whereas if that spacecraft needs to maintain its orbit, we may need a different mode to use thrusters in a way that it does not need to be as stable in its pointing, but needs to be extremely stable in a closed-loop sense, so as not to lose control of the spacecraft. We want to quantify the disturbance environment and use that information to both select the spacecraft control type for each mode and to select and size attitude control hardware for each of those modes. And we're generally going to aim at using as small a complement of hardware to meet all of the mode requirements as possible. Then we'll determine the determination and control algorithms, and of course we have to iterate with the rest of the spacecraft design team and document our design. I'm not going to go into this slide in detail. It had a lot of very good information though that I wanted to be available after the fact. But typical requirements may involve general pointing requirements involving the targets. We want to understand what accuracy is required of the system and what stability is required so that the images are collected correctly and with blur low enough that science goals will be met or payload goals will be met. We need to know the attitude knowledge requirements, the requirements on maneuvering or slewing. We need to know how quickly the spacecraft needs to acquire the sun and or ground communications, because those are often limited by battery size or solar array size or other needs. And we also have to have requirements on safety, on safing the spacecraft in the event of a flaw or fault in the design, and reliability of the entire system as a whole. Let me go a bit into detail on this one. We want to know what level of reliability or redundancy should be employed for recovery from anomalies. And that reliability and redundancy go hand in hand. If you have a spacecraft that needs to be extremely reliable, then it's likely that you'll use redundant components in the attitude control system and other subsystems to achieve that reliability. A spacecraft that is allowed a higher risk profile may not need any redundant systems at all. We need to know what the ACS needs to do in response to an anomaly. Generally, the question is, does it need to safe itself as carefully as possible, or should we attempt to collect as much data during the anomaly as possible, so it's fail-safe or fail-operational? And we need to know what level of stability is necessary for the reliability that we are going to get. All right, let me talk about the disturbance environment. Spacecraft are affected by a number of external disturbances, and there are four main sources of those. Solar radiation pressure is a force that is applied that the spacecraft experiences, and if the center of that pressure is not aligned with the center of mass of the spacecraft, then a torque results. Any residual dipole on the spacecraft can cause a magnetic torque if the spacecraft is low enough in the atmosphere, close enough to the magnetic field, that is. Gravity gradient results when the center of gravity of the spacecraft is different from the center of mass, and I'll have an image a little bit later to point out what that means. These four main sources, depending on the target profile and the attitude control modes used, and the altitude of the orbit, may be secular or cyclical. We'll get into detail on that in a little bit. I won't go into much more detail on internal disturbances, but I want to go through a list of them because they are often very important. Mechanisms such as a moving solar array or instruments that have moving parts are often the largest disturbances that we see on a spacecraft, but we generally know what they are very well in advance and can design an entire system to deal with those disturbances effectively. Thermal snap occurs when a large flexible structure goes from being very cold to very warm, coming out of the shadow of the Earth and into the sun. Misalignment and quantization in actuators is another big source of error when actuators are being used, such as in an orbit control mode where thrusters are being used to change the linear momentum of the system. But if they're not aligned carefully, then they create disturbance torques that have to be dealt with by the controller. Propellant motion can be important sometimes, and other times can be totally negligible. And there are other minor sources. Astronauts on the ISS can cause some vibration. Outgassing from the various polymers that are used, like the thermal blanketing. And differential IR emission can even be very important for extremely precise missions, where certain surfaces output IR at a different rate than other surfaces. And that can create an IR radiation profile that does not align with the center of mass. All right, I'm going to quickly change over to a different presentation mode so that we can see this upright. Okay, are we seeing that correctly? Okay, excellent. This is an image that shows the relative strength of the four different external disturbance torques that I was mentioning. On the left, the orange band represents the solar radiation pressure. In general, solar radiation pressure is increased or decreased for a given spacecraft configuration only by being closer to or further away from the sun. And so most spacecraft in Earth orbit are going to experience solar radiation pressure at about the same level. And so that band is relatively constant and then gets deeper as it gets closer to the sun. So if that can serve as a good example, we'll take a look at the other three. Atmospheric drag is often negligible above 700 to 800 kilometers, but it can be by far the largest disturbance in very low orbits, such as the ISS's orbit. Magnetic field torque is stronger than atmospheric drag at higher altitudes, but does not increase as quickly as drag does as you go down to lower altitudes. It is instead much more similar to gravity gradient. They both decrease with the cube of radius from the center of the Earth. Of course, gravity gradient can also be experienced around objects that don't have magnetic fields, such as a spacecraft in lunar orbit or in orbit around planets with weak magnetic fields. And there are also spacecraft that fly at Lagrange point orbits. An example of that, there are two dark blue ellipses near the top center. Those represent the Lagrange 1 and Lagrange 2 points. L1 is usually said to be the one that's between the sun and the Earth, and L2 is usually said to be the one that's on the other side of the Earth from the sun. And they're about 1.5 million kilometers away from the Earth, so they really only experience the solar radiation pressure of these four disturbance torques. And that's when some of those smaller internal disturbance torques can become the most important thing to consider. All right, I mentioned that external disturbances can be cyclic or secular. In these images, we've got a spacecraft that looks something like a camera with a flash on top of it. Imagine that flash part is a solar tab, so it has no mass, but it does cause solar radiation pressure. And therefore, when it's sticking out to the side, such as in the top here, I can use an arrow here, such as in this configuration, there's a torque into the screen, and on the opposite side, there's a torque opposite that. So what you get is a cyclic torque that builds up for part of the orbit, but then gets canceled out, and so momentum that builds up due to the torques only builds up to a certain level in each direction, positive and negative. So in this case, the tab, the part that is the additional, that's providing the additional solar pressure torque, is always pointed at the Earth. If we have the same configuration, though, but in an inertial configuration, we see that the torque would always be pointed out of the paper, out of the screen, and therefore we'd have a secular accumulation of momentum, and we would need to find some way of removing that angular momentum from the system eventually, or the spacecraft would not be able, its actuators would not be able to overcome the momentum at some point. So, because of cyclic and secular disturbance torques, we do need to manage angular momentum on the spacecraft. There are different ways of doing this. We can use magnetic torque rods, magnetic coils, to constantly remove small amounts of momentum. This works really well in low Earth orbit and not so well as you go up in altitude. We can use thrusters to occasionally remove large amounts of angular momentum from the spacecraft, but usually that disrupts whatever operation is occurring, and so that has to be balanced against the mission needs. I'm not going to go into all of the detail on this slide, but again, I wanted the information to be available. This is a list of different attitude sensors. On the left margin, you see high update rate and low update rate. Now, it's interesting, when I inherited this slide, the line was between rate gyro and star tracker. So the rate gyro is able to give very high update rates, and because it drifts, we need slow, occasional attitude updates to correct it. Well, star trackers are increasingly fast, and they're getting to the point that some trackers really have a high enough update rate that gyros end up not being very important to the mission. Some slower updates may come from fine sun sensors or from Earth sensors, but because of those fast and increasingly more effective star trackers, we're seeing star trackers taking the place of a lot of other sensors in a lot of contexts. Magnetometers, though, are needed for using those magnetic coil, the magnetic-based momentum management schemes, and so there's not really a good substitute for them. Actuators. I mentioned the magnetic torquers. Those are generally wires wound around an iron core, and they provide a torque in the same because they serve as electromagnets. And as I said, they're only useful in low to mid altitude orbits, the same orbits in which magnetic torque disturbance is a concern. Reaction wheels and control moment gyroscopes provide very smooth disturbance rejection. They can be sensitive to low temperatures, and so often deep space missions can't depend on these wheel-based actuators. Instead, they have to depend on thrusters. They're useful. Thrusters are useful in just about any flight regime you could imagine. They are great because you can use them to control the orbit as well as the attitude. They require expendables. The propellant does get used up. And also, they not only do they usually disrupt operations because they must be aligned with the direction that the orbit needs to be changed, but they may cause vibrations because of their sharp impulse, and that those sharp vibrations may take long enough to damp that they can cause a problem. Large missions, you'll often see a combination of these actuator types. Very briefly, I'll go through this chart. Attitude determination is used to take the sensor data from the sensors that were in the earlier list and process that into an estimate that the spacecraft control system can use. Attitude knowledge is the level of certainty associated with that process. As I said before, determination may be done real time, or it can be done later. Really, either of these types of attitude determination could be done either on board the spacecraft or on the ground, but typically you see real time being done on the spacecraft, and post-processing definitive attitude estimates being provided on the ground. Single-axis attitude estimation is good for the spin axis of spinning spacecraft. But even for spinning spacecraft, three-axis attitude estimation is becoming useful, and therefore overall spacecraft regimes, the three-axis attitude estimation is more common. An example of a spinning spacecraft that uses three-axis attitude estimation is the Magnetosphere Multiscale mission, which will launch in 2014. There are 4 spinners, and they fly star trackers to determine their attitude. So they know their attitude at all times throughout the spin cycle. Error budgeting. It's important to understand all the sources of attitude error and of pointing error that can occur on a spacecraft. Some sources come from the mechanical subsystem. They can only determine the alignment of certain sensors and the instrument to a certain level with the structure. And so we have to apportion some amount of the total allowable error to the mechanical subsystem. Typically, the attitude control system ends up with a certain amount of error allowed, and we use that to determine what attitude control methods we're going to use. I think I'll skip through this so that I can spend more time on later slides, but I want to encourage people to just remind people to ask questions throughout the presentation, and if you want me to go into more detail on this in the questions, I'd be happy to. In selecting which kinds of control methods we want to use, an early question that needs to be answered is, do we need active control for accurate control and stability, or can we use a passively stabilized system and rely on the fact that disturbance torques are very low to give us a stable enough platform to do what we need? The image on the top right corner demonstrates gravity gradient torque being used to point a satellite in its preferred orientation. The top of the satellite is further away from the Earth's center, and therefore it is pulled less sharply, less strongly than the bottom of the satellite, which is closer to the Earth's center. That gradient causes a torque that will tend to align the spacecraft's primary axis, principal axis of inertia, principal moment of inertia, with the nadir, and that has been used on many spacecraft in the past as a passive stabilization system, and therefore no actuators are needed. There are other kinds of stabilization. There are also passive dampers that can be used in spinning spacecraft to keep nutation down to a minimum. Active control is three-axis control where you're using sensors and actuators in combination to provide accurate pointing of the entire system. It can also be used to supplement passive stabilization. Passive stabilization can be a way of saving energy, and then small adjustments are made to that preferred orientation to damp out any disturbance, any motion caused by the other disturbances. Controller design analysis summary. So we talked earlier about the sorts of things that might go into controller requirements. Those requirements are generally going to say that the control system must be stable, and in addition to being absolutely stable, we want to see some kind of relative stability demonstrated either through linear analysis methods or through some other means. The speed of the response, though, has to be reasonably fast, and then the control system has to reduce the errors to zero or to some very small value, and so in that sense, performance can be set against the performance requirements can compete with the stability requirements. Controller design steps. We are all dependent on the spacecraft moments of inertia, which is often one of the quantities that is least well known early in the spacecraft design process. So we have design methods that are not dependent on having that exactly right early on. Often we include the spacecraft moment of inertia as a database value so that we can update it as we understand it better, more accurately. Given whatever the inertias are, whether we're close to prolate, oblate, spherical, we choose appropriate sensors and actuators. We model all of those things, and using those models, we design a controller based on the requirements. The last bullet here, construct a prototype physical system, is not done as much as it used to be. It's often quite possible to rely entirely on computer modeling because of the increases in computer speed and the ease of use of today's simulation tools. Of course, as with any control system, we are interested in the transient response as well as the steady state performance of the system. Excuse me. I'm going to talk a little bit about different attitude control algorithms. Attitude dynamics are inherently nonlinear. The Euler equations that describe attitude dynamics have a cross product that means that you have nonlinear dynamics. But in most applications, for a spacecraft, we can linearize the dynamics, and so we often use linear controls for controlling spacecraft. In some cases, we can use linear control techniques for every control node on the spacecraft with small adjustments made to deal with the nonlinearities of quantization. Let's see. So linear control makes analysis of the discrete systems simpler than if we used nonlinear techniques. If rotations are about an eigenaxis, then we may only need to design a single control loop. Otherwise, we may control each of the three axes, roll, pitch, and yaw, with a separate loop and allow them to either work in tandem or to alternate their commands. The TRIM spacecraft, for example, would command the x-axis one cycle, and then the y-axis the next cycle, and the z-axis the third cycle, and then repeat that process. Proportional integral derivative control, PID control, is usually implemented in software, whereas it used to be that that sort of control could easily be implemented using circuits. We often use PID for zero momentum systems because the disturbances are very small but variable. We may be able to get sufficient accuracy without using the integral term to remove the steady state error associated with constant disturbance torques. In other situations, though, there is a disturbance torque that is constant for long enough that an integral term is needed to remove those disturbances. Nonlinear control methods such as sliding mode and feedback passivation are sometimes used. The WMAX spacecraft used a partial form of feedback passivation. It fed forward the expected gyroscopic torques to linearize the attitude dynamics. That spacecraft was a zero momentum spinner, so it spent all of its time, all of its observation time spinning at a high rate, and so that's why the gyroscopic feed forward was needed. Control of thruster-based systems may be simplified with nonlinear control as well. And as I said before, performance must be balanced against stability requirements. Here I want to talk a little bit about jitter. Sensitive instruments have requirements to avoid blurring. Jitter, which is the term that we use for attitude dynamics that occur at a higher frequency than the controller bandwidth, the jitter has to be very carefully analyzed before launch, because when a spacecraft is vibrating in its vibrational modes, there's no way to damp it on orbit except to just wait for it to damp out. Most of the damping that occurs on modern spacecraft actually comes from the harness, the wires, and their insulation. So you can see that that's not going to provide a great deal of damping. We typically assume 0.1 to 0.3% damping values. The image shown here is actually on-orbit jitter observed in a test of the Solar Dynamics Observatory. This jitter is driven by several sources, but it's mainly driven by the high-gain antenna gimbal stepping. So our software prevents gimbal movement here in these pink areas just before the images are going to be taken, which is the blue area. And then as soon as the image is done, the instrument informs us that it's okay to step the high-gain antenna, and these circles indicate when steps are being taken. As you can see, it doesn't take long before the steps cause jitter to increase by quite a lot. But because of that pink area where the software suppressing the gimbal movement, the image doesn't have, the jitter is well below the limit for the image registration. So here are some examples. Hubble Space Telescope has a mass of 11 metric tons, and its system is a 3-axis stabilized system, 0 momentum. So that means that it generally attempts to make sure that it has all of its momentum, all of its angular momentum removed. Whatever disturbance torques there are, the momentum that builds up because of those is removed as soon as it can be. The accuracy required for HST is 7 milliarc seconds, which is in SI terms 34 nanoradians. The sensor it relies most on for attaining that accuracy is the fine guidance sensor, which is actually a custom-built interferometric star camera just for Hubble. And its main actuators are control moment gyros. The Hubble actually has no thrusters because, as many of you are probably aware, the space shuttle was used to boost it if that was ever necessary. Next example, the Solar Dynamics Observatory is 3 metric tons. It's also 3-axis stabilized, and it's a 0 momentum system in the sense that we try to keep the momentum low, but in order to avoid certain jitter problems, we predict what momentum buildup will be a month in advance, and then bias the momentum in the opposite direction from that buildup so that wheel speeds can be kept low and they won't contribute too much jitter. So the SDO has an accuracy requirement of 10 microradians, 2 arc seconds. We use guide telescopes that are attached to the instruments, but we also have 2 star cameras and a digital sun sensor, which act in a 2-for-3 Kalman filter-based voting scheme, such that we can lose any one of those 3 instruments and still be able to meet our requirements. Our actuators are reaction wheels and thrusters. We don't have any magnetic actuators because SDO is at a geosynchronous orbit and therefore too high above the magnetic field to get any real torque out of those. Third example, ST5 was 3 spacecraft that were each 25 kilograms. Some of the press reports reported that ST5 satellites were birthday cake sized or wedding cake sized, so very small spacecraft. They are spin stabilized, and I failed to fix this slide. I apologize for that. I'll fix this before we post these slides so that you can see the accuracy of the ST5 system. Here's a list of some references that are specific to spacecraft attitude dynamics and control. Feel free to check those out at your leisure. And I am ready to take questions.
Well, thank you very much, Scott, for sharing your knowledge and your insights into spacecraft attitude control. That was a very interesting talk, and it has generated several questions. I guess the first question I'll pass on to you is maybe you could take a couple minutes to describe some of the software-based tools that you and your colleagues use for the design and analysis of spacecraft attitude control systems.
Certainly. One tool that's very popular is MATLAB and Simulink. We used Simulink for the SDO mission because our flight software developers wanted to reduce some of their testing load and code review load by using Simulink's automatic code generation abilities. We developed an entire high-fidelity simulation using Simulink, and then the parts of the simulation that represented the controllers themselves, the PID controllers that we used, or the PD controllers that we used for the different modes, those were coded according to the flight software team's recommendations so that they could use them for automatic code generation. So that's a popular tool, and it's used quite widely. Some people prefer to write their own simulations. We have quite a few people here who over the years have developed their own tools for dealing with certain analysis questions. One is called SPAD, which is solar pressure analysis determination. That tool does ray tracing on a spacecraft model to determine the center of pressure of the spacecraft relative to its center of mass, and then it determines what the solar pressure torque would be in every attitude. That's been a valuable tool over the years. A more recently developed tool is able to do some of the same things, but it makes use of newer modern graphics cards to do parallel processing to do that ray tracing. That's called FreeSpace. FreeSpace is actually able to do that solar radiation pressure calculation at the same time that it does real-time or faster than real-time simulation of the spacecraft dynamics. We increasingly depend on simulations for our analysis as we get harder problems to solve, problems that just don't yield to typical linear analysis methods. But we still attempt to do the best we can to linearize each of our systems to understand our relative stability in terms of gain margin and phase margin to the extent that that is applicable to any given problem. So we got Nichols plots, Bode plots, and those sorts of things in tandem with the computer-based simulations.
Well, thank you for that answer. Let's see. There's a question here from Ames, and I think it has to do with. Person says, perhaps I missed it, but near the beginning of your talk, you mentioned that there's a difference. The difference between the center of gravity and the center of mass creates a disturbance. I think
right.
that's when you were talking about. Go ahead. Okay.
Let's go to. Here we go. So in this image, the top left image, I didn't make it clear that I was referring back to what I said earlier in the talk. But this is the cause of gravity gradient torque. And this image doesn't show the difference between the center of gravity and the center of mass, which it could have. But because the gravity pulls less on the top of the spacecraft than on the bottom, we actually end up with a center of gravity integrated over the whole spacecraft that is lower than the center of mass, but offset from it, until we get to the preferred orientation. And in that orientation, when the spacecraft is along that dotted line, that dotted image, the center of gravity still lies below the center of mass, but it ends up being aligned with the center of mass and the Earth's center, and so the torque is 0 at that point. Incidentally, spacecraft that are stabilized only by gravity gradient will in fact see slow oscillations because there is no process by which the gravity gradient motion can be damped. And so whatever offset you start with, the spacecraft will oscillate back and forth at pretty much that amplitude unless some active control is applied. I hope that answers the question.
I think it covers where the person was coming from. Yeah, I recall some of the early missions that we put up with the long booms, right, and the tip masses to affect the gravity gradient stabilization. And my understanding is if you work the physics of it, the system like that can stabilize in 2 orientations, right? Either possibly upside down. So it's kind
That's right. It can stabilize upside down. Yes.
Yeah. Well, thank you. There's a couple more questions. I think we have sufficient time here to go over that. I think this member of the audience was picking up on the one of the points you made about more prevalent use of star trackers these days. So it's a two-part question. One is there a trend, do you see a trend towards more gyroless systems? That's part A. And part B then is, it appears to me, I guess I'd like you to comment on this, it appears to me that Earth sensors are being used less these days, probably in favor of star trackers. So maybe you could take a swing at those two questions.
Yeah, let me answer the second part first. I would agree. My perception is that in new spacecraft designs, star cameras are competitive with Earth sensors in terms of price and in terms of accuracy, but they're much less dependent on establishing a certain attitude with the spacecraft to start with. So let me give an example. The TRIM spacecraft that I mentioned, the Tropical Rainfall Measurement Mission, it has an Earth sensor. That Earth sensor is designed to be very accurate, but it can only be very accurate when it is at a very, very specific altitude. As it turned out, the sensor was slightly misconfigured, and so did not give exactly the altitude that was needed. And that eventually, TRIM is a very long-lived mission. Eventually, the science team also wanted to change the altitude of the spacecraft to, and the Earth sensor was moved out of its favored altitude range far enough that it couldn't meet its attitude determination requirements. The TRIM team was able to come up with a new Kalman filter to use additional information that was available to meet the requirements, but that Earth sensor eventually was not able to do the job. Star Tracker would not have any problem at all in that situation, because it doesn't. The star trackers of today generally can acquire from a lost in space situation within seconds, if not milliseconds. So the first part of the question: are we moving to more gyroless systems? That I would not say is as much of a general rule. I think that on one hand, we've got gyros that are very accurate but very expensive in the millions of dollars range. But on the other hand, we've got MEMS gyros, which are very inexpensive and they're inaccurate, but they do provide information. I think that as we move towards smaller spacecraft, we're going to see more use of those small MEMS gyros and just ways of dealing with the errors that those MEMS gyros provide. But some missions are just going to need the accuracy that's provided, the rate accuracy provided by a gyro. If, for example, a mission needs to accurately track not just attitude, but it needs to follow a specific attitude rate trajectory, it's really going to, the analysis is going to be much more robust to show that the controller is going to be effective and meet all performance requirements before launching if a gyro is part of the system, some kind of a direct rate sensor is part of the system. That's a point to make generally. When a spacecraft is launched, you're done. It's going to do as well as it can from then on. In some other systems, we're able to test something out and then bring it back and improve upon the design. But for one-off spacecraft design, we have to rely on robust analysis methods to guarantee performance.
I agree with you about the, thank you, Scott. I agree with you about the point you made about the MEMS gyros. I think if we can find ways to compensate for their performance over wide temperature ranges, I think we're going to see more application of that technology. Low cost, small size, low power. Well, we have this will probably be our final question. It's a kind of an open-ended one, but I think it's an appropriate way to wrap up here in terms of the questions. We have a question that says, what are some of the technical challenges for the next generation GNC systems? And he gives an example, controlling via tethered systems. So maybe you want to take a crack at that, and then we'll probably draw this to a close.
Okay, I don't know a great deal about tethered systems. I do have some experience with formation systems where the spacecraft are not attached to each other. So I don't know what modern applications of tethered systems are. I know that several years ago there were thoughts about using tethered systems, using possibly a tether to generate power for a spacecraft. There was an experiment, I think maybe over a decade ago, where there was a tether, perhaps it was a spacecraft tethered to the shuttle. I can't remember exactly, but the tether broke because of the very high voltage that was generated through movement through the environment that the spacecraft was in, and it was proposed that maybe the tether could be used on purpose to generate a voltage and therefore generate some power. I'm sorry I can't speak more to tethered spacecraft in particular. I think that the direction that things are going is bigger and smaller at the same time. We see the James Webb Space Telescope with its solar shield the size of a tennis court. That is what's needed to address the astronomers' need for really high quality, high accuracy infrared observation of the universe. On the other end, small spacecraft are increasingly able to do more because the processors and MEMS equipment are making it possible to have much more sophisticated control systems on board a very small spacecraft. And a lot of work is going on in that field as well. And combining those spacecraft in formations is another exciting direction that we could go.
Thanks, Scott. Well, as they say on Car Talk, it's happened again. We've run out of time. Thanks for responding to all those questions. As we kind of expected, we received more questions than we can handle right now. What I'll do is pass along these remaining questions to you, Scott, so that you can follow up with each of these individuals. And thanks for agreeing to do that. There's a particular question that's very specific about how to assess the robustness of an attitude determination scheme, and then there's at least one other question about getting some information about the ST5 attitude control system. So I think you'll be able to deal with those. And
that I see as something I owe you all, and I believe what I'm going to do is respond to all of the questions in a single document so that everyone can see what other people's questions were.
Yes, when people come in after the fact here to see your webcast, it would be good to have them all in one place. Very good. Mm-hmm. Okay, well, thank you. What I'd like to do now is make a general request of the webcast audience here today and the NASA GNC community of practice in general, and that is if you have ideas for other GNC webcast topics, or even better, if you're interested in presenting your own GNC webcast, please do contact me directly. I would appreciate that. Always looking for new material. This completes today's NESC GNC webcast. Thank you for participating with us, and I look forward to you joining us again in September for our next webcast event. Thank you.